All right, I want to continue with our lesson today. That we were working on before the fire alarm drill. So to solve this problem, we have 126 milligrams of glucose, which is C6H12O6. And we have 100 milliliters of solution. To determine molarity, again, the mnemonic that may help you is to put a triangle with a T in it. And we have molarity equals moles divided by liters. So we look at what's given in the problem, and we have milligrams and milliliters. And we can easily convert the milliliters to liters. And the way we do that is 100.0 milliliters. And we want to convert milliliters to liters. And the way we can do that is we know the relationship that 1 milliliter is equal to 10 to the negative third liters. So to make the conversion factor liters over milliliters, we divide both sides of the equation by 1 milliliter. This side becomes 1. That tells us this is a true conversion factor, and that's what we place here. The milliliters will become 1. We'll be left with units of liters, and so we have solved this part of our molarity problem. The answer for this would be 0.1000 liters. All right, for us to convert from milligrams to grams, and then from grams to what the ultimate unit we need is moles, here's our plan of action. Convert milligrams to grams first, and the way we do that is, again, pretty much the same principle used before. 1 milligram is equal to 10 to the negative third grams, and that's the beauty of the metric system, is we don't have to know all these different units. Milli means 10 to the negative third, whether it's milliliters or milligrams. So we'll start with what we have, 126 milligrams. Multiply that by 1 milligram in the denominator and 10 to the negative third grams in the numerator. The milligrams become 1. We're left with our units in grams, and we are at this part of our plan of action. So to convert grams to moles, we have to know the molar mass of the substance. And we've talked about molar mass before. We assume we have 1 mole of the compound C6H12O6 glucose, which means that we have 6 moles of carbon, 12 moles of hydrogen, and 6 moles of oxygen. Okay, we look at the periodic table, and carbon weighs 12 grams per 1 mole, and hydrogen is 1 gram per 1 mole, and oxygen, yeah, it's not the best oxygen there, right? Oxygen is 16 grams per 1 mole. All right. So 6 times 12, let's see, let me erase this up here so we got some room. 6 times 12 is 72 grams based on the carbon. 12 times 1 is 12 grams based on the hydrogen. And 6 times 16 is 96 grams based on the oxygen. So if we add this up, we get 180. So I'm going to put 180 here. 180. Let's erase that and try that again. 180 grams. We'll put a decimal here to say we know this to 3 significant figures over 1 mole. Okay. So let's go back up here. And let's put in what we have. We know that the moles is 126. So let's calculate this part out. Let's erase this. So let's get a calculator. And let's take 126 milligrams, multiply that by 1 exponential negative 3, and then divide by 180. All right. My calculator puts out 0.0007, but I need more significant figures than that. I need to have 3. This only shows 1. So I'm going to put this in scientific notation and see what we get. Well, it doesn't really change anything. I get 7.00 times 10 to the negative 4th moles. All right. So here's my moles. 7.00 times 10 to the negative 4th moles. And I divide that by the volume we calculated, which was 0.100 liters. All right. So when I divide 7 times 10 to the negative 4th by 0.1 times 10, 0.1 liters, I'm going to get for an answer 7.00 times 10 to the negative 3rd molar sucrose or glucose. And that would be my answer. All right, so let's see what the book gets. And it is 6.99 times 10 to the negative 3. So to one significant figure, we're in agreement. All right, so plus or minus 1 in our least significant figure. All right, the key here is to draw this triangle and then find out your moles and your volume. Moles and volume in liters. To do that, you'll get the right answer. All right, let's go on. Now, when we put sodium chloride in water, we said that it dissolved into sodium ions and chloride ions. These positive and negative ions act as charge carriers to shuttle electrons back and forth between the two electrodes here. Let me try a different color here. That didn't come out too well. Let's see. Different color ink. Let's try this yellow. So with these positive and negative charge carriers, they didn't work either. Let's try it again. Electrons are shuttled back and forth between these electrodes. There's an electrode here, an electrode here, and that completes the circuit. So the electrons can flow through the wire, through the light bulb, come outside the other side, and go back through like that. When a solution is able to conduct electricity, we call that substance an electrolyte. Now, in slide B here, we have a solution. Let's say it's sugar and water. Well, sugar doesn't break apart into ions. Sugar stays as C6H12O6. It does not break apart into positive and negative ions. So there are no charge carriers or no ions to shuttle electrons back and forth between the two electrodes. So we don't see a conduction of electricity. And therefore, sugar is considered a non-electrolyte. All right? So, electrolytes are substances that form positive and negative charge carriers that we generally call ions that shuttle electrons back and forth between electrodes and allows the conduction of electricity. Non-electrolytes do not produce positive and negative ions or charge carriers, and therefore cannot shuttle electrons back and forth between the electrodes, and therefore do not conduct electricity. Let's go back to a nice blue color. All right, next slide. So what happens when ions are formed? Well, here's a sodium atom, and we've talked about these before. The sodium atom would have 11 protons in the nucleus, 2 electrons in the first shell, 8 electrons in the second shell, and 1 electron in the third shell. The sodium loses its outer shell electron, and notice the ion is smaller than the atom. And the reason why is now you got 11 positive protons working on only 10 electrons, and we've lost a shell. So these shells, because they feel the pull of the nucleus, they shrink, and we've lost a shell. The sodium ion, therefore, is much smaller than the sodium atom. The chlorine atom, though, on the other hand, what it looks like, it's 17 protons in the nucleus, 2 in the first shell, 8 in the second shell, and 7 in the third shell. All right, there's my 17 electrons to go with my 17 protons. The chlorine is going to gain an electron, so that in the end it's 17 protons, 2 in the first shell, 8 in the second, and now 8 in the third. Remember the octet rule. Same thing up here. When sodium lost its outer shell electron, now it has 8 electrons in its new outer shell. Chlorine gains an electron. It's got more protons, higher electronegativity. Remember electronegativity. Chlorine has a higher electronegativity than sodium, so it strips this electron off the sodium and uses that electron to make the chloride ion. Now, the chloride ion is much larger than the chlorine atom because you've got 17 protons working on 18 electrons. So that last electron we added, not attracted to the nucleus that much. And so it really causes, and remember electrons repel each other, so it causes these shells to expand outward. And that's why the chlorine ion is much greater than the chlorine atom. It is the positive and negative charge of these two ions that form the ionic bond that creates the compound sodium chloride. So what does that look like? Well, before we get to what that looks like, let's look at some of the charges on the ions. Metal ions, remember there's a stair step through here that separates the metals from the nonmetals. Everything to the left of the stair step is a metal, and everything to the right of the stair step is a nonmetal. Metals form positive ions, nonmetals form negative ions. The group number will tell you the charge on the metal ion. Group 1 forms a positive 1 ion. Group 2 forms a positive 2. Group 13, remember we focus only on the number that's in the ones place, forms a positive 3. And again, why this happens is, let's look at aluminum. Aluminum has 13 protons, 2 electrons in the first shell, 8 in the second, and 3 in the third. Aluminum is going to lose all 3 of those electrons to get a full outer shell of 8. And now we only have 10 electrons and 13 protons, so aluminum becomes a 3 positive ion. So remember the group numbers tell you how many valence electrons. The metal will lose its valence electrons to get a full outer shell. And the nonmetals, with the higher electronegativities and the more protons in the nucleus, actually gain electrons to get a full outer shell. So like, look at nitrogen here. It's in group 15. Nitrogen has 5 valence electrons. We could look at it right here. Nitrogen, 15 protons, 2 electrons in the first shell, 8 in the second, and 5 in the third. Which one am I doing? I'm way off here. I've really lost it. Nitrogen, let's do this again. I don't know what I was thinking. Has 7 protons. I knew something didn't look right. 2 electrons in the first shell and 5 in the second. All right, there we go. Oh my gosh, I can't believe that. All right, so nitrogen being a nonmetal, large number of protons in the nucleus, higher electronegativity, will gain 3 electrons to get a full outer shell of 8. All right, and when it does that, it becomes a nitride ion in 3 negative. All right. So the nonmetals, what you look at the group number, look at what's in the ones place. It tells you how many valence electrons that atom has. But the nonmetals are going to gain electrons to get that full outer shell of 8, to become isoelectronic with a noble gas. So these gain 3 electrons, group 15. Group 16 gains 2 electrons to get a full outer shell of 8, and group 17 gains 1 electron. But remember, the electrons are negatively charged, so we're adding more negative charges. That's why the nitrogen ion, or the nitrite ion, is a -3 charge. All right. The transition metals, this is the roughest because you can't just look at the group number and say what the charges are going to be. So these in here, you generally have to memorize. The most important ones out of this group are the iron and the copper, the mercury, the silver, and then the tin and the lead. Those are probably the most important ones to know. All right, so how do we name these compounds? Well, for the metallic cation, like sodium chloride, you name the metal by its full name, sodium. And the anion ends in an IDE, so we call this sodium chloride. And that IDE tells people we are talking about the Cl negative ion and not Cl. This is highly reactive. This substance you swallow every day in the form of table salt. All right, so they have totally different chemical properties, chlorine and the chloride ion. So the chloride tells us it's bonded with something else. So let's erase this. So how would you name this compound? Well, it's a metal with a nonmetal. It's an ionic compound. All right, it's ionic. If it's ionic, you name the metal by its full name, magnesium. And you name the nonmetal by its, you start with oxygen, drop the gen off of oxygen and make it oxide. All right, so let's erase that. All right. Again, metal with a nonmetal, you name the sodium by its full name, and the bromine becomes bromide. And we get sodium bromide. All right. This table shows polyatomic ions. Polyatomic ions are where we have 2 or more different elements bonded together with a charge. And these are the most important ones. All right. So you'll probably be referring to this page when you take your quiz or exam, so you may want to bookmark this. It's best to memorize these. They're not as hard to memorize as you think. I memorized sulfate. If you knock an oxygen off of it, it becomes sulfite. I memorized nitrate. If you knock an oxygen off of it, it becomes nitrite. And then the rest of these you pretty much just memorize. So acetate, bicarbonate, like in your house you probably have some Arm & Hammer baking soda, which is sodium bicarbonate or sodium hydrogen carbonate, and there's the, so that looks like this is a chemical formula. All right, so this is what you put in your cookies so that they rise a little bit. So what happens is when you put this in your cookies and you heat it up in the oven, this bicarbonate ion decomposes and generates carbon dioxide gas, and that gas is what lifts the cookie up and makes it rise. If you don't put any baking soda in your cookie, it just flattens out like that. Never rises. All right? So polyatomic ions, 2 or more different atoms or elements bonded together with a charge, and you'll be using this to name compounds. So what will happen is I will say, write the chemical formula for calcium nitrate, which is a common preservative in foods. And you're going to go, okay, calcium is a +2 metal ion, and nitrate is a polyatomic ion with a -1 charge. And you're going to say, what do 2 and 1 go into? 2 and 1 go into. And you're going to say 2. And you're going to say, I need 1 calcium, and then you need 2 of the polyatomic ions. So you put that all in parentheses and then put a subscript 2 out. A 2 out like that under it. All right? That makes sense. It's 2 of these -1 ions to combine with this 2 positive ion to give us an electrically neutral compound, calcium nitrate. All right, let's go on. I'm not going to erase that. Let's go on and do a different one. All right, name of this compound, again, you see it's a metal. It's a polyatomic ion called the hydroxide ion. And the metal would form what charged ion? 2 positive. There's a mistake here. 2 positive. It's in group 2. The name would be magnesium hydroxide. And the chemical formula for this should be MgOH2. This is incorrect. There should be a 2 around that. All right? You know they've made a mistake. Look at magnesium on the periodic table. It's in group 2. Forms a positive 2 ion. All right, what's the name of this compound? Well, you got to recognize this is a polyatomic ion, all of that. And then there's your nonmetal ion. So what's the charge on that polyatomic? Well, you know the nonmetal bromide is out of group 17. It forms a negative 1 ion. And if they've written the chemical formula correctly, this ammonium ion ought to be a positive 1. So let's see. Ammonium is a positive 1. And again, this is called the ammonium, not ammonia. I see a lot of students do that. This is the ammonium ion. All right. So the compound is ammonium bromide. All right, we've talked about this before. What happens when we put table salt in water? Well, here's the salt crystal here. It's like those little crystals you see in your table salt. When you put that in water, the water gets in between the sodium and the chlorides and forms a cage around the sodium ion. And notice the slightly negative oxygens or partially negative oxygens orient themselves towards the positive sodium ion. Like charges repel each other, opposites attract. So this is an opposite, partially negative with this positive. Down here, the partially positive hydrogens orient themselves towards the negative ion, the chloride ion. And so it creates a cage around these ions so that they can't get back together. And that's what we call dissolution, or dissolving. Now eventually you can exceed the energy that is used to separate the two, and you can cause a saturated solution where, yes, the salt will just start piling up in the bottom of the glass. But initially, when you first put some salt in water, it will completely dissolve. And this is what happens. It breaks apart into these 2 ions in solution. All right. Again, positive ions called cations. Remember the T there tells you it's positive. And then anions, like an usually means something negative. Anions, negatively charged. And water, because it's polar, it has that positive and negative end, it's able to break apart the sodium and chloride ions. Or the word we use is dissociate. All right. So this table shows the solubility rules. All right. So we talked about this the last time too. All nitrates are water soluble. All chlorides, most of them are water soluble except for silver and some mercury. Sulfates are water soluble except for strontium, barium, and lead. All right. And all sodium, potassium, and ammonium compounds are water soluble. So what I do is I just draw a line right here, and I memorize everything that's soluble and assume everything else is insoluble. So there's not much to memorize if you think about it's just from here up. The only thing that's a little difficult is the chlorides. You're thinking they're all soluble, but there are exceptions. Same thing with the sulfates. There are exceptions. But notice the strontium and barium are both out of group 2. So really, this is the only one you have to memorize outside of group 2. Not as much memorization as you think. Again, I'd probably bookmark this page because you'll probably have to come back to this during the quiz or exam to say, hey, what's soluble and what's not soluble. Okay, covalent molecules in solution. So we've talked about this. This is sugar. This is C6H12O6. And you go, well, how do we get that? Well, there's one unit here and there's another unit there. All right. Well, actually, this is a different sugar. This is well, it's still, no, it's C6. 1, 2, 3, 4, 5, 6. All right. So this is a sugar molecule. It does not dissociate into ionic compounds. It stays intact as one whole unit. And so because it doesn't form positive and negative ions, it doesn't conduct electricity, and it's a non-electrolyte. All right, here is the rule of thumb. This is important to memorize. Like dissolves like. Ionic compounds will dissolve other ionic compounds. Covalent compounds will dissolve other covalent compounds. And polar covalent compounds may dissolve ionic compounds. So polar covalent will dissolve polar covalent. Covalent will dissolve covalent. Ionic will dissolve ionic. And then the other one is polar covalent, like water, has the ability to also dissolve ionic compounds. So in this picture, we have the polar covalent water, and we have the strictly covalent oil. And so polar covalent water is not going to dissolve covalent oil. So that's why we see this, there's no mixing here. Here's the oil, here's the water. Now, if I wanted to dissolve the oil, what would you dissolve the oil in? Well, if instead of this being water, it was gasoline, gasoline is a covalent compound, then the oil would dissolve in the gasoline. And we do that. If you ever use a two-stroke engine where you have to mix the oil and gasoline together, like maybe in a weed eater or something like that, you use gasoline to dissolve the oil into the water. Or maybe you've got really oily hands and you've poured kerosene on your hands to get the oil off. Not recommended, but I do see people do that. So you say, well, maybe I go in and I use soap to get the oil off my hands. Well, soap is a special thing. It creates micelles, which have a polar end to the molecule and a non-polar end. The polar end is on the outside, and it mimics the water's polarity, so the whole soap molecule dissolves. But on the inside of that soap molecule is where the oil is trapped, on the non-polar end of the molecule. So what I'm saying is that on a soap, you have your oil, and then what happens is the soap surrounds the oil like this, and this is a non-polar end. The non-polar ends orient themselves towards the oil, and then the molecule of soap is really long chain, and on the end of it, it's polar, like that. So it's polar on the end. So it's a long chain molecule, and at the end of the molecule, it's polar. So the water sees the polar outside like that, and so it dissolves it. In fact, that's the way your detergent works in your laundry. You put in detergent, it dissolves the oils off your clothes, like maybe from your skin, or maybe you've got some oil or dirt from you've picked up throughout the day. So you put detergent in the water, and the detergent fixes itself to the oil, and the outside of that large micelle is polar, so that dissolves in the water and it goes out with the rinse. And then you add more water to make sure that you get rid of the extra detergent that wasn't used. I mean, there are still detergent molecules in the water that are not used, so they're out there like that. So hopefully in the rinse you get rid of that. Now if you add too much soap to your washing machine, maybe you don't get rid of all the soap, so your clothes have got soap on them. And you know if that happens, like they always show that demonstration on some commercial where somebody washes their towel and they think it's clean, and then they put it in water and start agitating it, and all of a sudden the towel foams up. It's because they added too much soap to begin with, and not all of it was used. All right. So the rest of this chapter is talking about contaminants in our drinking water. So we have a contaminant level goal, and we have a maximum contaminant level. And this is the type of thing you'll see on your water assays, or when you get a readout from your water company saying what's in the water. For this part, I recommend you read the book. I'm not going to spend a lot of time on this. This shows nitrate concentrations, and large nitrate concentrations do have a detriment on our health. You can see at some places it's really great, generally where we have agriculture, because nitrates are used as fertilizers. So that's what this map is showing. Do want you to understand how we come up with drinking water. We have an intake pipe. For us, it's the Kentucky River. We have a pump that pumps water out of the Kentucky River. We have screens that screen out large objects like twigs, branches, cans, things like that. We add a flocculating agent. Now, what the flocculating agent does is it sticks to generally nonpolar substances, and it causes those substances to float to the top up here. So you got a paddle here that agitates the water with the flocculating agent attached to the substances in the water, and they generally come off the top. And then we have a settling tank where if anything settles off of the bottom, we take that out. And then we pump what's left. So we've got the particles that were lighter than water with the flocculating agent. We've got the substances that are heavier than water in the settling tank. And then we take that water and we pass it through a coal or sand filter. That's to get even more minute particles. And some chemicals and things like that that are detriment to our health. Those get trapped in this coal or sand filter. And then we pump the water, we chlorinate it. That kills off any bacteria left. And then in America, most of the time we want our teeth enamel to get hardened, so we add a little bit of fluoride in our water to protect our teeth. Not all places have fluoridated drinking water, but we do have that in Lexington. We pump that water into these storage containers, which are you can see that over at the Arboretum, the big UK water storage tank. That develops pressure, right? So when it comes out of this, it forces the water, gives us the water pressure to force it into your house. So when you turn on the faucet, it comes out with some force. All right. So understand this diagram of how we generate drinking water. We're talking about making fresh water from salt water. Yes, this is done. We have desalination plants in California, and many places that are located near the ocean and do not have an adequate source of fresh water have to desalinate their water. But the problem with this, it takes quite a bit of energy to do that. It's much easier to pull it out of a river or a lake and treat the water than it is to actually remove the salt from the water. Most of the time, the desalination requires either a nuclear power plant or some fancy membranes, filters, which have to be replaced and are not very cheap. Okay, so distillation, this is the way the desalination plant that works off of a nuclear reactor. We use a nuclear reactor's energy to boil salt water, and the boiling point of water is much less than the boiling point of salt. So the salt's left behind. The water goes through the water vapor as steam goes through a condenser. There's cold water pumped in this jacket here that surrounds the distilled water, and that causes the steam, the distilled steam, to condense back into the liquid, and we collect it over here. Now we can also do that through a solar panel, but using solar power, the speed of the the reaction or this process is much slower. So here's where we were talking about a membrane. So instead of using a nuclear reactor to heat up the water, this is generally more cost effective. We use a pump to pump salt water into a reaction vessel, and you have all of these dissolved particles, sodium ions and chloride ions, and then you have a membrane, and this membrane does not allow the sodium ions or the chloride ions to pass through. It only allows the water to pass through. So we constantly use a force to force water through the membrane, and then the excess ions come out here. Now some water comes out here too, that's why it's called brine. Brine is actually a very concentrated salt solution, so we do lose, not all the water makes it across the membrane. So first of all, we're using a lot of water to do this. And this concentrated brine, most animals cannot live in it, so it's either going to have to be diluted or recombined with salt water before it's put back into the ocean. The membrane costs quite a bit of money, and so those have to be replaced. Every once in a while these get filled up with substances and they stop working. And we know this starts getting clogged up because if we got a pressure gauge here, the pressure all of a sudden starts shooting up. That tells us we need to replace the membrane. It takes thousands of these reaction vessels to make enough drinking water for most populations. All right. We call it reverse osmosis because in general what happens is this water would flow from the lower concentration to the higher concentration until these two solutions became equal. All right, and to give you an example of that, if you look at a cucumber, here's your cucumber. What do we do with cucumbers? We put them in a brine solution, which is a salt solution, and the water from the cucumber goes out through the skin of the cucumber, which is the membrane, and what we get is we get this crinkly looking thing like this that we call what? A pickle. So that's generally what happens. The solvent will flow from the less concentrated to the higher concentrated solution until both things are of equal concentration. But what we're doing is we're using a high pressure pump to actually force the water back this way through the membrane. That's why it's called reverse osmosis. So it takes energy to drive the pump, it takes a specialized membrane, and again, it is a cheaper way of doing it than using a nuclear desalination plant, but it's still much more expensive to do this type of processing than just processing lake or stream water. All right, so in third world countries, many times the water looks like something like that. It's got a lot of sediments in it and bacteria. So scientists have developed these life straws. And that's what this is. It's a straw that contains multiple filters in it to filter out harmful bacteria, and it allows people to drink creek water, stream water, puddle water safely. What it does remove is bacteria, viruses, and parasites. What it may not remove are heavy metals like mercury, lead, cadmium, and so forth. So yes, it is a large improvement, but we're not quite to the same standard as we would have in our American drinking water. And again, the rhyme of the ancient mariner, water, water, everywhere. You've heard probably of this, not a drop to drink, nor any drop to drink. So here's the full passage here. All right, so that concludes Chapter 5. I hope you've watched this video. I would recommend that for sure, and I'm going to post this on YouTube. So watch this video before taking the quiz or doing the assignment. Thank you.